All right, welcome back to 25 through 29. Starting with question 25, let's review what Lewis dot structures are. Lewis dot structures, we're going to use dots to represent outer shell electrons or valence electrons. All right, electrons like to occur in pairs. We're going to put the least electronegative in the middle. So hydrogen is going to bond to carbon, and that will bond to nitrogen. Now, this guy has how many electrons? Hydrogen has 1, carbon has 4, nitrogen has 5. That adds up to 10. There's 2, 4, 5, 6, 7, 8, 9, 10. But unfortunately, when I do that, hydrogen has met the octet rule because he only has 2. Carbon, however, moving over so it doesn't look like carbon's bond. Carbon at this point only has 4. Nitrogen has 10. So we have to accomplish some sharing. Why won't that go away? All right, we're going to go in here and we're going to move these 2 electrons here and these 2 electrons there. So we end up with something that looks like this. Now we have 2 electrons around our hydrogen. Our carbon has 8 electrons and our nitrogen has 8, so everyone is happy. All right, the next guy. Phosphorus has 5 electrons. Chlorine has 7. 7 times 5 is 35. So we have a total of 40 electrons. Phosphorus is going to be bonded to 5 chlorines. So this is an expanded valence. And we've used 10 electrons. So we have 30 more to go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So, in all told, we have 40 electrons. This is the Lewis dot structure for phosphorus pentachloride. We'll talk what shape that is in a little bit. SEF. Selenium has 6 electrons. Each fluorine has 7. 7 times 4 is 28, plus 6 would be 34. We have 2 electrons, 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, and we're going to put 2 more on the middle as a lone pair. This is still going to give us a different geometry. It's going to be the same geometry as our phosphorus pentachloride. We just have a lone pair. Talking about XEF. XE, oh, wait a minute, that's a noble gas. How can that be? Well, it's because it's so big that if you bring the right element, i.e. the most attractive element, nearby, that fluorine can steal electrons. So we have 8 electrons in xenon. Each fluorine has 7, so there's 14. 8 plus 14 is 22. XE, there's 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. We have actually 3 lone pairs on that Lewis dot structure. Thiocyanide, we have sulfur has 6, carbon has 4, nitrogen has 5, and then you get 1 for the negative. So we have 16 electrons. Sulfur is bonded to the carbon, which is bonded to the nitrogen. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 12, 13, 14, 15, 16. Now, looking at that, we have enough bonds around sulfur and nitrogen, but not around carbon. So we're going to have some double bonds. Whoops. Oh, I didn't mean to erase all of that, poor guy. 2, 4, 6, 8, 10, 12, 14, 16. Is that what I needed? Yes. And sulfur has 8, carbon has 8, nitrogen has 8. So those are Lewis dot structures. Ionic and covalent bonds. Remember that ionic means you have a cation and an anion. Lithium, or a metal and a nonmetal. Lithium's a metal, chlorine's nonmetal. This is ionic bonds only. Sodium is a metal. Phosphate is a group of elements that carry a charge. This is a covalently bonded group of elements. So this guy has both ionic and covalent. Here we have metal and nonmetal, metal and nonmetal. Well, not two nonmetals, but not anything. It doesn't have a charge. And we don't have any ionic parts. All right, so this is our ionic and covalent bond. More Lewis structures. Ammonia, we have 5 plus 3 is 8. NH, H, H, 2, 4, 6, 8. Carbon, we're going to double bond to both oxygens. Oh, I have too many electrons on there, don't I? Good catch. Boron trifluoride is an interesting fellow. There are 21 electrons from our fluorines, 3 from our bromines, so that's 24. This would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now, looking at that, boron is breaking the law. He does not have 8 electrons, but funny enough, he's actually okay with that. He has 3 valence electrons. He's okay with giving one away. He just doesn't share completely. So he's kind of like an ionic and kind of not. SF6, sulfur has 6 electrons. Each fluorine has 7. 7 times 6 is 42. And 6 more would be 48. 2, 4, 6, 8, 10, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. So let's talk geometry now. When we talk about electrons, electrons repel each other. So they're going to orient in space as far away from each other as they can. If you have 2 bond areas, they're going to orient as far apart as they can. They'll be 180 degrees apart. If you have 3 bond areas, like that boron trifluoride, they'll orient this way with 120 degree angles. 4 bond areas, they will orient with 109.5 degree angles in this shape, which is hard to see when you're talking about a drawing on a piece of paper. 5 bonds, we get this interesting shape where we have right angles. We have 3 arranged just like our trigonal planar, and then 1 above and 1 below. And 6, we get 4 going this way and 4, well, that looks like it was the same way, but it wasn't. But we get 4 in a plane, and then 1 coming off the top and 1 coming off the bottom. So the question was, who has electron pair geometry, tetrahedral? Well, tetrahedral electrons mean they're going to have 4 bond areas. Either 3 bonds and a lone pair, 2 bonds, 2 lone pairs, but a total of 4. Nitrogen is bonded to 3 hydrogens and has a lone pair, so this guy is the tetrahedral. Now, is he actually a tetrahedral? No. His basic geometry is tetrahedral, but he has that one lone pair, so his name is trigonal pyramidal. Because he's a 3-pointed pyramid. Trigonal pyramidal. It doesn't spelled right, but you'll figure it out. The next one, carbon dioxide, has linear geometry. Boron trifluoride has trigonal planar geometry. SF6 has 6 bond areas. Is going to be this octahedral bond area. And SEF4, if we look back, he looked like this. And he had one lone pair, so he has 5 areas. So he fits in this trigonal bipyramidal area. With one lone pair, he would actually be the sawhorse shape. The next question asks about angles. Well, again, we can refer to drawing with this information in it, although the bond angles for trigonal planar are 120. Also, trigonal bipyramidal. So 120 bond angles are going to be in both this guy and this guy. Okay? The next question says, who's polar? Polar means, we've already talked about a water molecule being polar because he has unequal sharing. So anybody that has unequal sharing, well, that means they're not going to be symmetrical. Here, nitrogen is not symmetrical because there is an end that has nobody pulling on it. So there's going to be a dipole. This end will be negatively charged, this end will be positively charged. So he is polar. Here, tug of war, carbon's going to get pulled on equally by both sides, nonpolar. Here, the fluorines are all going to pull equally, polar or nonpolar, because it's equal. Here, these guys will pull equally, these guys will all pull equally, nonpolar. He's symmetrical. This guy, though, we have the one lone pair, so he's polar. Basically, if they have a lone pair, they're going to be polar. All right, 27, talking about resonance. We didn't do much of this in class. So let's draw the, oh my, we're getting long. We're going to stop now, and we'll put 27 on the next one.